Hello everyone. Today we are going to discuss two important techniques in image restoration. One is notch filtering and another one is inverse filtering. Both methods are used to improve degraded images, especially in biomedical imaging. Images from MRI, CT and X-ray often suffer from noise, blur, interference patterns. So our goal is to remove unwanted noise, restore original image quality. Today we will understand how these two filters work, their differences and where they are applied. Let us recall the image degradation model. A degraded image is formed due to blur caused by the system noise introduced during acquisition. Let us understand real-world problems in MRI. We get periodic noise interference in CT. Motion blur occurs due to a patient movement. In X-ray, we observe interference patterns. So the problems of structured noise, blur, loss of important details, important insiders. Some noise appears only at specific frequencies. So instead of removing everything, we need targeted solutions. Now let us define the core problem clearly. We need to remove periodic noise, restore degraded images. So the challenge is how to remove specific noise frequencies and recover the original image. This leads to two approaches. Target noise directly. It is used for notch filter, and a reverse degradation is inverse filter. So the problem is divided into two solution paths. Now we explore possible solutions. First is notch filter. It removes specific frequency components used for periodic noise. Second is inverse filter. It reverses the degradation function used for blur removal. So the notch filter used for noise removal and inverse filter is image restoration. We apply frequency specific correction, not general filtering. Let us understand the notch filter. A notch filter removes specific frequency points from the image spectrum. It is mainly used for periodic noise interference patterns. Instead of removing a full range, it removes only selected frequencies. So it is highly precise. This makes it very useful in biomedical images where noises appears in a pattern. Now let us see how notch filter works mathematically. At a specific noise frequencies, the filter value becomes 0. Noise removed. At all other frequencies, the filter value is 1, so signal preserved, so only unwanted frequency components are eliminated. This selective filtering ensures minimal loss of useful information and effective noise removal. This slide shows frequency response. We can observe sharp dips at specific points. These dips corresponded to noise frequencies, so the filter suppresses only those locations. Important insight from this slide is notch filter performs localized suppression, not global filtering. This is why it is highly efficient for periodic noise signals. Notch filters are widely used in biomedical imaging. In MRI, they remove periodic interference. In CT, they eliminated structured noise artifacts. And using this, it can provide a clearer image, reduced artifact, better diagnostic quality. So notch filters improve visual clarity without affecting important structures. Now let us move to inverse filtering. The idea is simple. If degradation caused the problem, we reverse it. We use here the G of UV is a degraded image. H of UV is a degradation function. By reversing the H of UV, we try to recover original input image F of UV. So the inverse filtering directly attempts to undo system effects. Let us understand how inverse filtering works. It removes the blur function H of UV from the degraded image. It recovers the original signal, but there are two conditions. H of UV should not be 0. So it is very sensitive to noise. So even small noise can get amplified. This makes inverse filtering unstable in practical cases. In this slide, we see the behavior of inverse filtering. It amplifies high frequency components. This helps in sharpening. But the problem is noise also lies in high frequency regions. So noise gets amplified along with the signal. So the inverse filtering improves detail but may increase the noise. Inverse filtering is used in biomedical imaging for motion blur correction in MRI and CT. Image sharpening and enhancement also used. The results from the inverse filtering, it restored edges, improved clarity, better visibility of fine details. However, due to noise sensitivity, it is used carefully. Now we have understood both filters individually. Before concluding, remember that real-world problems often require combining multiple techniques. So these filters are usually part of a larger restoration pipeline. For deeper understanding, you can refer these standard textbooks and research papers. Thank you.